Section 3.7 is all about function notation. In Chapter 1, we talked about functions. We looked at what makes something a function and how to identify a function. Now remember, a function is when x values do not repeat when you're given a table of values. So anytime x value is repeated, so you have the same x value going to two different y values, it is not a function. If you're given the graph, you run the vertical line test, which means as I pass vertical lines throughout the entire graph, if one of the vertical lines hits the graph in more than one spot, it is not a function. In this section, we will be talking about what kinds of words and symbols you use when you are using and talking about functions. So to start, you can name a function f and therefore write it in function notation. So for example, y equals mx plus b would be written as f of x equals mx plus b. So if you see here, they're replacing the y in our equation with f of x. And again, that's read as f of x. So what that means is I am calling this equation mx plus b, I'm calling that equation f, and the variable, this of x part, the variable that we are using in the equation is x. If it said f of a, that would tell me that the variable being used in the equation is a. So again, to repeat, f of x is another name for y, is read as the value of f at x, or simply f of x, and that will be typically how you will hear me phrase it. This does not mean f times x. A lot of kids look at that f parentheses x and think it means f times x, but again, it's read as f of x, and again, that just means that x is the variable that is being used in the equation. You can use any letters other than f. Most common letters used are G, H, and P. So again, those are just names that you can use to call functions. Example number 1, evaluate the function f of x equals negative 7x when x equals 7. Notice I put a side note in here and it says another way to write it is find f of 7. So notice that they are replacing the f of x, they're replacing the x inside of that with a 7, meaning you should substitute 7 in for x. So f of 7 is how I'd write that, is equal to negative 7 times 7. So again, I'm just taking this 7 and replacing the x in the equation with 7. So f of 7 would equal negative 49. The ordered pair that would go along with that would be 7 for the x value and negative 49 for the y value. Not that this problem asks you to do that, but just for clarification, that would be the ordered pair. If I were to graph that equation, I would have a point on the graph at 7, negative 49. Example number 2, for the function f of x equals negative 2x plus 4, find the value of x so that f of x equals 16. Remember, f of x is another way to say y. So when it says f of x equals 16, that's just saying y equals 16. So it's kind of like the opposite of the last problem. This time we're going to put 16 in for the f of x and then solve for x. So I'm going to have 16 equals negative 2x plus 4. I'll subtract 4 from both sides. 16 minus 4 is 12, equals negative 2x. Divide both sides by negative 2. 12 divided by negative 2 is negative 6. So the x value is negative 6 when f of x is equal to 16, or when y is equal to 16. So here again, not that this problem's asking you to clarify this, our ordered pair would be negative 6 comma 16. So that means if I were to graph this equation, y equals negative 2x plus 4, the line would pass through the point negative 6, 16. Example number 3, a bowling alley charges $5 to rent shoes and $4 per game. The cost after playing X games is given by f of x equals 4x plus 5. This makes sense because we are charged $5 no matter what, so $5 right off the bat, and only one time we're charged that $5. Then it said $4 per game. Now remember, the word per means to multiply. So I take 4 times the number of games that I'm playing plus the $5 shoe rental fee. The problem asks to graph the function and identify its domain and range. Notice I only gave you the option of graphing in the first quadrant because our x value represents the number of games. It doesn't make sense to have a negative number of games. And the y value, which in this case is f of x, represents the total cost. We will never pay a negative number for cost, so it didn't make sense to show the negative y-axis. So again, it only required the first quadrant to graph this. So to graph it, remember f of x is another name for y. So we can really just think of this as y equals 4x plus 5. That would mean that our slope is 4, but I'm going to say 4 over 1 since I'm going to be graphing it and I want the rise over the run. And the y-intercept is 5. I graph the y-intercept first. Notice I gave a graph that is counting by 5s along the y-axis and 1s along the x-axis. So I'm going to plot the 5 first on the y-axis. So there's my y-intercept, and now I'm going to go up 4 and to the right 1. Again, considering that I'm counting by 5s along the y-axis, I'm not going to go up a full unit along the y-axis since it's up 5 each time. So I'm going to kind of estimate and say up 4 is just below the 10 and over 1. So you can see there I counted up 4 and over 1, and I was just below where the y-axis said 10 since I didn't go up a full unit since they're counting by 5s along the y-axis. 2 points determine a line, so now I'm just going to take these 2 points and connect them with a nice straight line. And there's my graph. Notice I put an arrow because this can continue forever. So the domain is your x values and range are your y values. Now remember, x in this case is representing the number of games, and y, which in this case we're actually referring to as f of x, would be your total cost. So our domain x would be any number that starts at 0, since I could play 0 games, and really I could play an unlimited number of games. Therefore, for my domain, which represents the possible x values, I would start at 0, because again, I could just play 0 games, or I could play an unlimited number of games. My x values could start at 0 and go on forever. So I would say x is greater than or equal to 0, because again, I could play 0 games or an unlimited amount of games. So it started at 0, that's why it was equal to 0, and then greater than 0, because I could play as many games as I want. For my range, which again is your possible y values, the smallest amount of money that I could spend is $5. And if I have an unlimited number of games that I could possibly play, I would start at $5 and go on forever. So again, my range, my y values, would start at 5 and go on forever. So it would be y is greater than or equal to 5, because again, the smallest amount I could pay is $5, and if I play an unlimited games, I would have an unlimited amount that I would pay. Let's get into some more vocabulary. A family of functions is a group of functions with similar characteristics. So what this is talking about, when you look at the graph, they have similar shape. If you look at the equations, they have similarities about their x's and y values, like the x's are all being squared, or they all are being added to a certain amount, so that would be a family of functions. For example, functions that are in the form of f of x equals mx plus b constitute the family of linear functions. The root word of linear is line, so that tells you that if I graph any equation in this form, which again we typically see it as y equals mx plus b, if I graph any equation in this form, the graph will be a line, so it's called a linear function. Remember, this means that x is in the first power. There's nothing that's happening to the x. There's no square, there's no power on it. It is not being taken by a square root. It's not in the denominator. There's nothing weird or odd going on to the x value. So anytime x is to the first power and I graph it, I get a linear function because the graph is a line. I've included a graphic here, which is just a screenshot from your book, about the parent function for linear functions. It says the most basic linear function in the family of all linear function, called the parent linear function, is f of x equals x. So basically, they've just stripped down this entire slope-intercept form. They're saying the slope is 1, because there'd be a 1 technically in front of this x, and there is no y-intercept. There's no plus b part, so it'd be 0. So the most basic form of y equals mx plus b is when the slope is 1 and the y-intercept is 0. And it looks just like this. So I start at 0 and I go up 1 and over 1. That is the most basic form of a linear function. Again, it starts at 0, it has a y-intercept of 0 and a slope of 1 over 1. So I go up 1 and over 1, just like that. So y equals, or f of x equals x is your parent function for all linear functions or linear equations. Again, that is just slope-intercept form stripped down so that the slope is 1 and the y-intercept is 0. All other graphs that are lines are based off of this parent function y equals x. It may have a bigger slope like y equals 2x. It may have a plus 2, so like y equals x plus 2. Everything is just a modification of this parent function y equals x. If you think about your parents, aren't you just modifications of your parents? You're just other versions of your parents. You might look like them, you might have the same mannerisms as them, but you're just slightly different versions of your parents. So every linear equation is just a modified version of y equals x. In example number 4, we'll see the comparison of the parent function compared to a modification of that parent function. So again, example number 4 says graph the function. Compare the graph with the graph of f of x equals x. So remember, that's just y equals x. That is a graph that has a slope of 1, in this case 1 over 1, because remember you always want rise over run, and a y-intercept of 0. So let's first graph that. I always start with the y-intercept, so I'm going to start at the origin. If the y-intercept is 0, I'm going to start at the origin, so I'm going to put a dot at the origin. And then my slope is up 1 over 1. So now you can see that second point there. I could continue that pattern of going up 1 and over 1 and then just connect all of those points and draw a nice straight line. So that's what I'll do next. And there you have the parent function. So let's label that. The red graph is going to be our parent function, the y equals x, or f of x equals x. Now they want us to graph g of x equals negative 2x. Now remember, it's no different than when I call something f of x. We're just calling this equation g. So when I graph that, I first need to identify the slope, which in this case is negative 2, but I always want it as a fraction, so negative 2 over 1, and I still have a y-intercept of 0. So just like before, I'm going to start at 0, and then I'm going to go down 2 and to the right 1. This time I'm going to graph in blue. So first I'm going to graph that y-intercept of 0. So basically I just put a blue dot on top of the already red dot that was there, and now I'm going to count from that point down 2 and over 1. So now that I have my 2 points, I'm going to connect those 2 points with a nice straight line. And there's my line. So you can see here, this is still a linear function because I got a straight line, but it's just a slightly modified version of that y equals x. Since it was negative, my graph was now going downhill. And since my slope was negative 2 over 1, my graph was a little steeper. It went up and down a little bit quicker than it did on this one, even though one was going uphill, one was going downhill. Let's look at another example. So this one's part B. It still says graph the function, compare the graph with the graph of f of x equals x. So remember, that means that I have y equals x. That means I have a slope of 1 over 1 and a y-intercept of 0. So just like before, I'll start with the 0 on the origin and go up 1 and over 1 when I graph it. So you can see there I started at 0 and I went up 1 and over 1, and then I'll just connect those 2 points. And there we have the graph. And now I'm supposed to graph h of x, so we're just calling this graph h, equals 1/2 x. So just like before, I have a slope of 1 over 2 and a y-intercept of 0. I'm going to graph this one in blue. So I'm going to again start at the 0, and I'm going to count up 1 and over 2. So there's my blue dot, which again is just on top of the y-intercept of the other equation, the parent function, since they both had the same y-intercept. And now from that point, I'm going to count up 1 and over 2. So looking at that now, remember I start here and I count up 1 and to the right 2. I'll just connect those 2 points with a nice straight line. And there you have the red line versus the blue line. Remember, the red line was the parent function and the blue line was our modified version, 1/2 x. If you notice here, they're both straight lines because they're both linear equations. And since 1/2 was smaller than the slope of 1, our blue line was actually less steep than our red line. But again, they both had a y-intercept of 0, so they both passed through the origin. This last slide is just a graphic, again, that I stole from the book. I just took a screenshot of your textbook where they are comparing graphs of linear functions with the graph of f of x equals x. Now remember, that is the parent function. It says changing m or b in the general linear function g of x equals mx plus b creates families of linear functions whose graphs are related to the graph of f of x equals x, which is what we've been talking about. So if you notice here, they say if I start with g of x equals x, so there's your parent function, but now I'm taking something and adding it to that parent function, I get g of x equals x plus b. Adding this b into there really just moves it up or down. It still has the same slope because the slope is still 1 in front of that x, but if I add 2 to it, that would move the y-intercept up 2 units and I would still have that same slope. If it was x minus 3, I would move it down 3 units, so it still has that same slope, but I'm now just going through the y-axis at -3 instead of through the origin. Now it says if I have g of x equals m times x, so where m is something other than 1 like it was in the parent function, and it says when m is greater than 0. So that means I still am going uphill because my slope is positive, and if my slope is big, if it's a big number, I'm going to have a steeper line. If the number is between 0 and 1, so like a fraction, then I'm going to have a more shallow or less steep line. If your equation is g of x equals m times x, where m is less than 0, so like negative numbers, now our graphs are going to go downhill. And just like before, if that number is a big number like -3, then it's going to be steeper. If it is a number between 0 and 1, it's going to be less steep and not be so straight up and down. So again, all of these are just comparisons of that parent function, y equals x or f of x equals x. So slight modifications to y equals x will result in a slightly modified version of that line. So again, if you're adding something, it's going to move it up or down, depending on if it's a negative number or a positive number that you're adding to it. If your slope is greater than 0, it's going to still go uphill. It just might be a little steeper or not as steep. If your slope is less than 0, now it's going to go downhill. And again, if it's a bigger number or a smaller number, it'll determine how steep your line is. That's it for this section. Make sure you jot down anything you don't understand so we can cover it in class, and we'll see you then.